Okay, sample problem 10.5. If a child releases a 6.25 liter helium balloon in the parking lot of an amusement park where the temperature is 28.50 degrees Celsius and the air pressure is 757.2 millimeters of mercury, what will the volume of the balloon be when it has risen to an altitude where the temperature is negative 34.35 degrees Celsius and the air pressure is 366.4 millimeters of mercury? So in other words, we have a balloon. Let's put the balloon here near the surface. The balloon rises to some altitude. So it has new conditions. So I'm going to call the ground the first condition. So I'm going to say that on the ground, the initial pressure is 757.2 millimeters of mercury. That's a pressure unit. And the temperature is 28.50 degrees Celsius. Of course, this is a gas, right? So we're going to add 273.15. So 28.5 plus 273.15 is 301.65 Kelvin. Oops, sorry, let me come back to that. 301.65. Okay. And then we're told that the volume at the ground, V1, is 6.25 liters. Now, once we get up to altitude, it doesn't say what the altitude is, but it's up somewhere. So now we're going to have a new pressure. And so now the new pressure is 366.4 millimeter of mercury. You could actually figure out what the altitude is based on the atmosphere's profile. There's a pressure profile for the atmosphere. And so that pressure is about half, it looks like. Let's see, 6. Yeah, it's close to half. So you could figure out what the altitude is. T2 is negative 34.35, but we're going to add 273.15. So negative 34.35 plus 273.15. Remember, no Celsius in these gas laws. 238.8 Kelvin. And then they say, well, hey, what's this new volume? That's the question. Okay? So this is a little different than the previous ones. When the pressure, volume, and temperature are all changing, you use what's called the combined gas law. It's the combination of those three gas laws we just looked at. It's P1V1 over N1T1 equals P2V2 over N2T2. However, the balloon is closed. It's not opening or, so gas can't come in or out. So if gas can't come in or out, we simplify it to P1V1 over T1 equals P2V2 over T2. That's called the combined gas law, assuming that no gases can escape or enter the balloon, okay? All right, so it's not an easy thing to predict what would happen. What happens is if the pressure is lower at altitude, the volume will get larger. But if it's colder, the volume will get smaller. So those two counteract each other. So you really have to go through the calculation to figure out what's going to happen, okay? So we have the numbers. It's just a matter of figuring out how do we isolate V2. That's the algebra. See how we have V2 over here on the right? What I'm going to do is I'm actually going to make a little room over here and show you the algebra. For some of you, this is simple. For others, it may not be. P1 V1 over T1 equals P2 V2 over T2. We're trying to find V2. So what I'm going to do is get rid of this arrow. Is I'm going to say I want V2. So I want to get the P2 to the left side. I want to get rid of it on the right side in any case. So if I divide by P2, then P2 over P2 is 1. But if I divide it on the right side, I've got to divide it on the left side. So I'm going to divide by P2. And then T2 is in the denominator on the right side, and I want to get it over there, away from there. So I'm going to multiply by T2, because T2 over T2 is 1. And then if I do that on the right side, I've also got to do it on the left side. And there you go. T2 over P2 times P1 times V1 over T1 is going to be equal to V2. That's the only thing left over. Okay? So now let's put the let's put the numbers in. T2 is up here. So that's 238.8. P2 is up here. That's 366.4. P1 is down here. That's 757.2. Let me put that in parentheses. V1 is down here, 6.25. And then we need T1, right? T1's down here, 301.65. Okay. And then that's going to give you V2. Okay? So how are we going to do that? That's a lot of numbers there. So 238.8 divided by 366.4. 238.8 divided by, let's come back, 366.4. So we got a number there. Then we're going to multiply it by 757.2, and we're going to multiply it by 6.25. 757.2 times 6.25. Then we're going to divide it by 301.65. So divide that by 301.65. And there you go, 10.2. Now you'll notice I didn't do any of the units in there. That's a no-no. We got to do the units. But when we have a calculation with so many numbers, it's sometimes useful to show the units separately, just to make sure you don't get numbers and units confused. A 1 can look like an L, right? So what do we have in terms of units? Well, coming back over here, we have temperature units, which are Kelvin, right? Divided by pressure units, which are millimeters of mercury, times pressure units, which are millimeters of mercury, times volume units, which are liters, divided by temperature units, which are Kelvin. Kelvin over Kelvin is 1. Millimeters of mercury over millimeters of mercury is 1. Liters. So that means our answer is in liters, which is exactly what we would expect for a volume calculation, right? So in other words, this is what's happened. The balloon went up to a high altitude where it was colder and lower pressure. By getting colder, it should have gotten smaller, but by going lower pressure, it should have gotten bigger. Well, what happened? It started at 6.25, it went up to 10.2. That tells us that the pressure was a bigger factor, right? Because it got bigger. The lower pressure made the balloon get bigger. It was a bigger issue. And the reason is the change in pressure was more dramatic. The pressure went down by more than a half. 366.4 times 2 is less than 757.2. So the pressure went down a lot. The temperature went down, but not as much, right? If the temperature went down by a half, it would have gone down to 150 Kelvin. But it only went down to 238. So it went down, but not as much. Okay? So the result of that is the balloon is bigger at altitude.